How nuclear bombs work. A simple explanation. Introduction. Good day, everyone. Today, I'm going to explain one of the most powerful forces humans have ever harnessed: nuclear energy. Specifically how it's used in nuclear weapons. While this is a serious topic, understanding the basic science helps us appreciate both the incredible power of atoms and why nuclear weapons are so concerning to world leaders. Think of this as a journey from the tiniest building blocks of matter to explosions, more powerful than anything else humans have created. What are atoms? Let's start with the basics. Everything around you, your chair, the air you breathe, even you, are made of tiny particles called atoms. Atoms are so small that millions could fit on the period at the end of this sentence. Each atom has a center called a nucleus, which contains protons and neutrons packed tightly together. Think of the nucleus like a tiny, incredibly dense ball. Orbiting around this nucleus are electrons, like planets around the sun, but much, much smaller. Here's the key point. The nucleus contains enormous amounts of energy holding those protons and neutrons together. It's like an incredibly tight spring. If you could somehow break it apart or force nuclei together, tremendous energy would be released. The two types of nuclear reactions, there are two ways to release this nuclear energy, and they're actually opposites of each other. Fission means splitting apart. Imagine you have a very large, unstable atom, like uranium or plutonium. These atoms are so big and packed with particles that they're naturally wobbly, like trying to balance too many books in a stack. When you hit one with a neutron, think of it like throwing a marble at that wobbly stack. It splits into two smaller atoms. When it breaks apart, it releases tremendous energy and also throws out more neutrons. Fusion means combining together. This is the opposite. You take two very small, light atoms and force them to stick together to make a larger atom. This also releases enormous energy. This is actually what powers the sun, hydrogen atoms constantly fusing together. Both processes convert a tiny amount of matter directly into energy. Following Einstein's famous equation, E equals mc, that little c represents the speed of light, which is a huge number. So even a tiny amount of matter becomes an enormous amount of energy. Chain reactions, the key to nuclear bombs. Now here's where it gets really important for understanding nuclear weapons. Remember how I said that when a uranium atom splits, it throws out more neutrons? Well, those neutrons can hit other uranium atoms, causing them to split too, which releases even more neutrons. This creates what scientists call a chain reaction. It's like dominoes falling. One triggers the next, which triggers the next, and so on. But unlike dominoes, each domino that falls knocks down multiple others, so the reaction grows exponentially. In a nuclear reactor at a power plant, this chain reaction is carefully controlled. They use control rods to absorb some neutrons and keep the reaction steady. In a nuclear bomb, the chain reaction is allowed to run wild, releasing all that energy almost instantaneously. Fission bombs. The first nuclear bombs, like those used in World War II, were fission bombs. They work by bringing together enough uranium or plutonium to start that uncontrolled chain reaction I just described. The tricky part is getting enough radioactive material in one place, packed tightly enough for the chain reaction to work. Scientists call this amount the critical mass. If you have less than critical mass, the neutrons escape before they can hit other atoms, and nothing happens. But once you reach critical mass, boom, chain reaction. The bomb contains conventional explosives that compress the radioactive material into a tight ball, achieving critical mass. Once that happens, the chain reaction spreads through the entire mass in microseconds, faster than you can blink. The explosion creates incredible heat, millions of degrees, hotter than the center of the sun. This creates a massive fireball that vaporizes everything nearby and sends out intense radiation and a powerful shockwave. Fusion bombs. Fusion bombs, also called hydrogen bombs, are even more powerful. They use the energy from a fission bomb as a trigger to force light atoms, like hydrogen, to fuse together. Remember, fusion is what powers the sun, but it normally requires incredible heat and pressure. The fission bomb provides exactly that. It creates temperatures of millions of degrees. It's hot enough to force hydrogen atoms to overcome their natural repulsion and stick together. When they fuse, they release even more energy than fission. This is why hydrogen bombs can be hundreds of times more powerful than the original atomic bombs. The devastating effects, the destruction from nuclear weapons, comes in several forms. The initial blast creates a fireball that vaporizes everything within a certain radius. The intense heat can cause severe burns miles away and start fires across entire cities. The explosion creates a massive shockwave, a wall of compressed air moving faster than sound, that can flatten buildings and throw vehicles like toys. Nuclear weapons also release deadly radiation. Some of this radiation is immediate and can be fatal within hours. Other radioactive particles settle as fallout and can contaminate large areas for years. The combination of heat, blast, radiation makes nuclear weapons uniquely destructive, capable of destroying entire cities with a single bomb. Conclusion: understanding how nuclear weapons work helps us appreciate why they've shaped international relations for decades. Science is fascinating, but the implications are sobering. These weapons represent both human ingenuity and our capacity for destruction. The same nuclear science that powers these weapons also gives us clean energy, medical treatments, and scientific research tools. Like many powerful technologies, it's not the science itself that's good or bad, but how we choose to use it.